Okay, all right, let's get started. Good morning, everyone. We need to have our lecture starting at 10 a.m., isn't it, to draw more students in. 9 a.m. is too early. Anyway, let's get started while more people wander in. We finished off yesterday by briefly introducing one of the core principles of object-oriented design, which is encapsulation. We talked about encapsulation being hiding the state of the object, okay? So how do we do that? So in order to hide the state of the object, we basically, object-oriented encapsulation principle, what does it recommend? It recommends that you make the instance variables or the attributes private so that it can only be accessed within the object instance. So any other objects that wants to have access to the state of the object, that wants access to these instance variables, must only ever access these attributes through the methods. Yep?
If you should always make all your fields private in the first place, then why does Java have public fields at all?
Why do we have public fields? Public is just an access modifier that can be public in Java. It can be applied to a class, it can be made to a method, it can be applied to an attribute. Okay, so in general, you can define in Java, for example, you might have a scenario where you might want to make a field a public, static, and final, almost like a constant in the other languages. All right, so that could be. But generally, as a rule of thumb, okay, you would have most fields as being private, and public is an access modifier. I mean, just as talking about Java, as I said yesterday, Python does not strictly enforce the encapsulation. However, in another programming language like Java, we have what we call as access modifiers, and as you correctly pointed out, the use of the access modifier called public makes the field directly accessible. So why have a public? Well, public is an access modifier that's not just applicable to the field. So Java makes available 4 types of access modifiers. It says public, private, protected, and default. Okay? Now, the use of the public can be done with a method or a class, and you can have in Java fields which are public, but generally they're more likely to be used for fields which are static, and they tend to be final, but methods need to be public. Okay, that's just a language thing. But with Python itself, we have no such strict enforcement. So when we talk about strict enforcement, what it means that Java being static typed, when you actually define these public access modifiers, it not only checks the types, it looks at the access modifiers. So if you try to actually define a variable which is private and you try to access it from another object, this is detected at compile time. Okay? However, we have no such enforcement in Python, and all you can do is to say politely to the clients, hey, these variables are private. Can you not access them directly? We recommend that you access it through the access it through the getter and setter methods. So it's kind of like almost like a design by contract kind of philosophy. You're delegating the responsibility of adhering to encapsulation to the clients. So what are the consequences of not adhering to encapsulation? Well, you have already indicated your intent to keep your variables private. If you still have clients directly accessing, there could be potentially undesirable consequences. I'll show you an example in a moment. Okay, but just before that, the notation in UML as to how we want to represent, to show private and public. As you can see, we have the class diagram, which shows the name of the class followed by the attributes and the operations. The minus symbol before the attribute indicates that the attributes are private, and the operations indicate, which with the plus before them, indicate that these operations are public. Okay, so in our class account, we define 3 private variables, name, minimum balance, and balance, and then we have got what we call as a setter and getter methods. in addition to some other instance methods such as deposit and withdraw. All right, so why is it so important to adhere to, we talked about in, okay, so let's just look at this example in here. Okay, take a moment to actually study that example closely. All right, actually I might do, as we type it up, well, I'll just switch over to my laptop. Okay, all right, so what are we going to do? Yesterday we looked at how to define a class in Python. We said that in order to initialize the state of the object or assign values, initialize values to the attributes, we define a constructor. A constructor is a special method that has this 2 underscores in it followed by 2 underscores in it, and we can go something like name, min balance, and I can say self dot name equals, again, I'm indicating my intent. It's not, sorry. What is happening here? Oh, let me try that again. Oh, maybe I didn't plug in. Sorry. Thank you. I should always turn back and check if it's displaying. Is that better? Yes. Okay. All right. I started off saying we're defining a constructor is of the form. It's a special method which goes 2 underscores in it followed by 2 underscores, followed by the parameter self, which refers to the current object instance, and any number of a set of values that you can use to assign the state of the instance variables. So we go min balance equals the input and something, perhaps you had a balance, for example, and you can go min balance. Okay, all right. Okay, so let's now try to define some setter methods, setters and getters. So we can go define get balance, and remember you must always pass in self because you want to know which object instance is this instance method being invoked on. Return self dot balance, and I can go and define another method called deposit self amount. We could do something like self dot balance equals, or that's a compound operator. What it's saying is the balance is just equal to the balance plus the amount. And let's do another method which is called as withdraw. All right, and what this does, now this is going to do a check which says that if the amount to be withdrawn is less than the current balance. So it's going to say if self.balance minus, sorry, that should change to amount. It doesn't really matter, it's the name of a variable, so I just, that amount is less than or equal to, I could have another business rule saying that when you withdraw the amount, you must not, your balance must not become lower than the minimum balance, say for example, and we can go something like minimum balance, then I have the habit of putting in braces because in Java you always put braces, so you can say something like print minimum min balance must be maintained, something like that. Else you simply happy to we just need to make sure these. One thing with Python is a bit fussy about if you try to use spaces and tabs, you need to stick to one convention, otherwise it's going to throw a balance minus equals the amount, all right? So that's all good so far. All right, so let's just make sure and we actually compile that. Count test. All right, and if I actually run it, okay, it's sweet, no problems, it's all compiled. All right, so what I've done is defined a class account with a constructor with some getter and setter methods, and actually there's no setter methods. You can add them if you want to, and some couple of other instance methods, deposit and withdraw. Now I'm going to try to actually create an instance of. Now, what are the parameters that I need to pass to the instantiation of the object? I need to pass in some name and I need to pass in a value. Okay, so this is good. Let's say, actually, I want to make it, let's say the minimum balance is 100, and now I'm going to try to withdraw say 75, and let's save and run that. It should say, it gives me, it does the check. Your minimum balance is 100. You're trying to withdraw an amount which is going to make the balance lower than the minimum balance required. Okay, so your program works as expected. But see what happens, because Python does not strictly enforce the encapsulation, there is nothing stopping someone to actually go and do this. Okay, knowing that the minimum balance is 100, what is stopping somebody from doing that? It will work fine. Okay, so now if you could try to go and say balance is now, and so format, you can go self dot, sorry. All right, okay, hang on a second, what did I go? Sorry, my mistake. A1 dot balance. Okay, see now what it's done. Okay, it's allowed you to actually go and violate a business constraint. So this is what I mean when you try to recommend to the objects, to the clients, that they must adhere to encapsulation and they violate the encapsulation, they can have undesirable consequences. Okay? So in Python, this is very important to bear in mind. You can only make a recommendation, and if you violate it, the code does not promise, it does not guarantee the behavior. Okay? So there is a contract in here. There's a design by contract. There is an obligation between the caller and the callee. Okay, so the callee says, if you call my method adhering to the formal contract that we have, then I guarantee you the right behavior. However, if you violate the preconditions, if you violate the formal contract, then you can have unexpected results. It's like you have a contract with the bank saying that when you withdraw money or when you release a check, you expect that you have adequate funds. However, if you release a check which does not have adequate funds, the consequences are unknown. The bank could be kind enough and just simply charge you an overdraft fee and release it, or they could completely refuse it. It's the same analogy here. So, did you have a question? What did I do? Oh, yeah.
And with the withdraw, so statement with the else, you've got the underscore self-dot.
Oh, okay. Yep. But how did it not? It is, you are right. Okay, sorry about that. Okay, all right, so what happens? So encapsulation enforces that the balance is hidden, and we have seen breaking encapsulation can actually render the state of the object to be invalid. Okay? So when you talk about, when you study COM 2511, we devote a whole lecture on talking about how important it is to maintain the class invariant. Class invariant is a condition that upholds the business constraint. And one of the business constraints here is the minimum balance must never drop below 100. Okay? However, by doing something like this, you can actually violating the business constraint, and by not adhering to the contract, you are making the class invariant invalid, and the object state could be rendered invalid. Another reason why, so one reason we've seen is preserves the object state, and encapsulation, as I said before, helps to treat you the methods that are provided by a service provider like a black box. So you only ever think about what does this method do, and you never have to worry about how the method is implemented. The consequences of that is it increases the usability of that particular component. That component which exposes its attributes only through the methods is it defines what we call an interface. So the interface becomes the contract or the communication interface between the caller and the callee. By enforcing that all your clients only ever communicate with the object instance through that interface, the caller only ever has to worry about what are the services provided by the interface, not how these services are implemented. So the consequences are it increases the usability of the component of the services provided, and also because the implementation is internal to the object instance, if you were to modify the internal implementation, the internal representation. So for example, if you had a method called getBalance which returned returned the balance which is currently of type double, okay? It's probably not a great example to use for the primitive, but for some reason, if you internally decide to represent you change the data type, or you modify the internal representation of balance, but as long as the returned type, the data that it's actually returned type still adheres to the contract as outlined in the interface, you can go and freely change the internal implementation of your component. So what this protects is it isolates the change to the component that is being modified, and you don't actually have a cascading effect on all the other components. If other components were to directly access the internal object state of your component, by modifying the internal implementation, you've just triggered off a cascading changes, and all the other components that are directly accessing it would have to go and change their code. However, if they only access through the interface and the interface is not changed, and you change only the internal implementation, keep the interface the same, the change is isolated to your component and does not cause a ripple down effect. So these are probably the three most important uses of encapsulation. First, to preserve the object state. Two, to provide an interface that isolates any changes to the component and does not cause a cascading or ripple down effect. And third, increases the usability of your component. Okay? All right. By the way, the slides are uploaded, so if anyone wants to have a look on WebCMS. Okay. All right, so so far what we've been discussing about are the properties of the components or the itself, the objects itself. So we looked at how to logically group object instances into a class. We looked at how to define the constructors and initialize the state of the object instance. So now we start looking at relationships or collaborations between the different object instances. So when you are collaborating, so for example, we want to look at relationships such as an instructor teaches a student. a university enrolls a student, a professor teaches a course offering, a computer lab contains computers. So you can see how now we're trying to associate two different objects and we're trying to make them collaborate with each other. A dog is a type of pet. Now these relationships, we can now start seeing a pattern in here. They can broadly be grouped into two categories, which we refer to them as inheritance or association. So how many of you have done biology in high school? Some of you? Yeah? So you must be familiar with the taxonomy hierarchy, right? But when I talk about taxonomy, do you understand? There is a class animal kingdom. There's a plant kingdom and animal kingdom. Under animal kingdom, you have class Animalia. Underneath that, you've got mammals, reptiles, amphibians. So you can see that there is, in your taxonomy, there is a hierarchical structure. So under amphibians, you have got frogs, and the mollusks, you have got, I don't know, crustaceans and whatever. And under mammals, you've then got other species and subcategories. But what you essentially, what the taxonomy is doing, it's building a hierarchy of the animal and plant kingdom based upon the properties. So at the very broad level, you categorize them into plants and animals, and then you came down, and the animals, you broadly categorize them into vertebrates and invertebrates based on the property, one common property, that they all have they've got a spinal cord, and these don't. And then you came down to vertebrates, and you broke them down into amphibians, aquatic animals, whatever that name is, and mammals, again based on what have you done. So the mammals, the aquatic and the amphibians all share the same characteristic, that they have a vertebrae, but in addition, they have their own specific specialization. So when you go into amphibians, these are species that live on both the land and water, and they have their own characteristics. And then you go on to the aquatic, they have their own characteristics. They have, they're able to live underwater, they have special respiratory organs or gills, for example. So the idea that I'm trying to draw here is that you can do something very similar when you're modeling the real world objects, when you tend to have a generalization of concepts. So for example, you might have a class called as pet. Then you say a dog is a type of pet. So notice the word I use, is a type of. So just like I can say an amphibian is a type of invertebrate, or a mammal is a type. So you're saying they're a kind of, so we're using the same idea. So a dog is a type of a pet. A parrot is a type of a pet. But so you start off by having a generalized concept called a class called pet, where you probably want to record the type of the species, you want to record the color and the age of the pet. But then what if you want to start storing some additional attributes for the specialized subclasses? So with the dogs, you perhaps want to record if the dogs love cats or not. With the parrots, you want to record if they the age of the parrot, the color, and what it can do, or anything like that. And if it is something else. So if you wanted to record more specialized attributes for your subgroups, that's when inheritance. So inheritance is all about when you can actually model a relationship between two classes, when one class will represent a more general concept, and this more general concept, or this more general class, is what we refer to as the base class. And then you have the more specialized class, which is the subclass. And you see everyday examples of this. So we created an account, a class called as account, but really, when you look at it, there's no such thing as an account. All accounts have in common, they have an account number, and they have the person associated with the account. But then you start looking down into the subtypes of the class account. You have a savings account, you have an overdraft account, you have a check account. Each of these, what's common among all these three subclasses or all these three subgroups is that they all share an account number, they all share a first name, last name, and perhaps an address. But a savings account has an additional feature associated with it called a bonus saver interest. An overdraft account has a, for example, an overdraft fee associated. A check account could have perhaps a monthly account keeping fee. Okay, so inheritance models use inheritance whenever you can model an is a kind of relationship. Like a savings account is a type of bank account, a dog is a type of pet, a manager is a type of employee. Okay, so these are examples. So how do we represent them again in UML before we move on to looking at some code in Python? So on the slide up there, you have two classes, as we have seen before. There is the name of the class, the attributes, and the methods. We use a solid line with a triangle at the top to model the inheritance to show that this class savings account is a kind of or inherits from the base class account. So when we use the word inherit, the subclass, also known as the derived class, okay? So you can use the derived class or the subclass, inherits all the attributes and the methods that are defined in the parent class, also known as the base class or the superclass, okay? Now, the derived class can do two things. Firstly, it can extend the base class by adding its own special attributes and methods. So for example, it's adding on the saver interest attribute and adds on the method called as calculate interest. Okay, so that attribute and method is specific to the savings account class. Okay, that's one thing it can do. But it can also do, override a default behavior provided by the parent class. Okay? Let's say for the, in the account class, there is a method that we defined a method called deposit and withdraw. Okay? So when we come into the savings account, remember, because it is a derived class, it inherits the methods of the parent class, it inherits the deposit and withdraw method, but perhaps the behavior of the withdraw method, there needs to be an additional check needed, or some other, there is its own specialized behavior. The derived class wishes to extend or modify the behavior that is provided by the parent class, then it can actually override the method in the parent class. Okay? So let me go over this. The derived class can do two things. One, it can extend the base class by adding its own specialized attributes and methods. Two, it can choose to override the methods in the parent class to provide its own specialized implementation. So with inheritance, the derived class can do one thing. It can do an extension, or it can override. Okay? And we're going to be looking at how both of these are actually done. Any questions so far? Okay, so this is the first kind of relationship that we are going to be looking at. This is another classic example that is actually used to demonstrate the idea of inheritance. So we have a base class called a shape, and it defines a name and an area. It's got two attributes. It's got some setter and getter methods, and it defines a method called getArea. Okay? Now that's a very good example of method overriding. Now the shape itself, what could it provide in the implementation of getArea? Does a shape know how to calculate the area? If you did not know what kind of shape it was, then how would you provide an implementation for the getArea method? So then we have a subclass or a derived class rectangle which inherits from the shape class, so it inherits the name and the area attributes. But what it does, it provides its own implementation for the getArea method. So the rectangle has two additional attributes, the width and the height. So in the getArea method, it can now say, return the product of the length and the width. So imagine if you had another shape like a circle that also extends from shape. So circle can also inherit from shape, but inheriting the shape, it inherits the name and area, but it will override the getArea method to provide its own implementation, which is, so it must have an additional attribute called the radius, and it would compute the area as pi times r. Okay, so see how the method overriding starts becoming useful. So you have a base class that serves as a placeholder to encapsulate common attributes and common methods. But then it defines an additional method. So you might ask me, then what is the purpose of having the getArea method in the base class? If the shape does not know how to implement the getArea method, why should I have the getArea method in the base class? Can anyone think of a good reason why I might still want to have the getArea method?
To specify that all child classes need to implement it?
Exactly, precisely. Thank you very much. That's the perfect answer. So later on, we will be talking about an idea called abstract classes, where the purpose of an abstract class is purely to encapsulate some common attributes and methods, and it can define some default methods in there, like getArea, but when the child classes inherit the abstract class, they are forced to provide an implementation for the getArea method. And that's the reason you would have the getArea method in the base class, even though the shape class does not know how to implement. So you might have a default implementation in there which says return 0. Okay? Does everybody understand? So you still want to have the getArea so as to enforce all the derived classes to provide an implementation for the getArea method. Because if you now define a new shape called a triangle, and it's possible that the programmer who's developing the triangle class forgets to provide an implementation in the getArea method. So if the client were now to call a getArea on the triangle, they would have undesirable results, or they would not have the right result. Okay? All right. So that's how we model inheritance using a UML diagram, and we talked about derived classes being able to do things. They can extend the attributes and the behavior of the base class. They can override the behavior in the parent class. Okay? All right. So let's switch back and we can start looking at some code on how to actually code inheritance. Okay, so okay, all right. We can define that now. So what I'm doing is defining a savings account class, and in Python the way I say savings account extends from the account class is by putting the name of the class within parentheses. So you might ask, what actually happens here? When I actually don't specify anything, the class account is actually extending the object class. There's a parent class called object, but if you don't put anything, it's implicit that the class account, all classes, if you don't actually specify any inheritance, they extend a base class called as the object. So in class savings account, I can now define my constructor. Okay? So I could say define a constructor as before, takes in a name and an amount, and perhaps the interest as well. And now, I can copy the code in here to initialize the name, minimum balance, and the balance. But the question is, if savings account is actually inheriting from the parent account, it can delegate the responsibility of initializing those common attributes to its parent class. So how do I invoke the constructor in the parent class? So I invoke the constructor in the parent class by using the name of the parent class followed by, I just call the init method. Okay? And I say the name, add the amount. And once the parent class has initialized the name and the minimum balance and the balance, I can now go to self.saver interest equals assigned to the interest. Okay? All right? And let me say, I can define some getter methods. So I can say get interest, and we look at return self.saver interest. Okay? Is everyone happy with that? So what I've done is defined a class savings account, which extends the class account. I have introduced a constructor, but instead of initializing all the variables, what I want to do is call the constructor in the parent of the superclass. To do that, I invoke the constructor in the parent class, and I do that by account.the constructor, passing in the name and the amount. Okay? And then I go on to proceed to initialize its own specific variables. Okay? Any questions so far? All right? Okay. Let's now go and I'm going to remove this and so I can say something like S1 equals savings account, and Sam pass in 200, and let's pass in the interest. Okay? And print, I could say, no, sorry. And I'll say S1 dot get balance, comma, S1 dot get name, for example. Okay. What did I do? Sorry. What did I do here? Have I got, don't I have a get name? Okay, sorry. I don't have a define get name. Return self dot name. And that should hopefully work. Yes, it worked. Okay? All right. Any questions? Okay, inheritance is a very important concept to understand, and you will be seeing practical examples of this. And later on, the next thing I'm going to be talking about is the other kind of relationship, which is association, and an important and very important decision that you will need to make when modeling your class diagram is when you're looking at two classes, two objects, you need to work out, now, is that going to be an association or is it an inheritance? Okay? And that's something that comes with experience, And by looking at the problem domain, analyzing the behavior of the analyzing the collaboration, then you decide whether the relationship between the two classes or between the two group of objects, is that an inheritance or is that an association? Okay? All right. Any questions? Does anyone want me to go over this again? All clear on inheritance? Yes, can I have a show of hands? Who is crystal clear? Okay, right. All good? Okay. All right, so how are we going for time? Okay, we are going good. So what I might do is, okay, let's just go into the other relationships, and then if we have time, we'll come back into abstract classes, because I do want to get into modeling as well. So, okay. Now, the second type of relationship that I want to talk to you about is what we refer to as an association. Now, this is a kind of collaboration where you don't see a is a type of or is a kind of relationship between the objects, like in a taxonomy, okay? But you more have a link, an association, a link between two things, like a person drives a car, a professor teaches a course offering, a student enrolls in a seminar, okay? Now, there are three types with the association itself. First of all, when you can see a link or an association between two classes that is not an inheritance, you say class A is associated to class B. Then you start thinking about what kind of association is this? Now, with the professor teaching a course offering, that's just two objects collaborating with each other. However, you think about perhaps a car which is made up of some wheels and it's made up of an engine. What's the difference between these two? With the car, when you say a car has an engine, a car has wheels, what you're seeing there is a kind of container relationship, okay? So, and the next question is, if it is a container relationship, then what happens when the container is gone? What happens to the parts? Okay? So, do the parts disappear? So think about what happens when the car disappears. What happens to the engine and the wheels? Do they serve a purpose? Okay? Now that's a question that you can again think about. Can I actually use the engine in another car? Let's look at another example. A book with its pages. A book has or contains a certain number of pages. All right? What happens, again, if you rip away the book, if the book burns, what happens to the pages? The pages are gone as well. Okay? So the idea that I'm getting at, we're starting at looking at a relationship between two objects. That's not an inheritance. So we say, okay, that's an association. Class A is associated with class B. Then we look at the nature of the association. Is it just a collaboration or is it a container type of relationship? Okay? If it is just a collaboration, like a professor teaching a course offering or a student enrolling in a seminar, you just say it's just a general association. However, if it is a container type of relationship, like a pizza is made up of toppings, a book is made up of pages, a car is made up of an engine, that's more a container has a relationship where there is a whole part relationship. There is a container and it has parts. And that's what we refer to either as an aggregation or a composition. Okay? So I've introduced three ideas here. We have association, aggregation, and composition. When we realize, when we are exploring the nature of the association and we feel that there is some kind of a container relationship, then we say this is more than just a mere association, it's either an aggregation or a composition. Okay, now is it an aggregation or is it a composition? Then you go on to the next question, which I was talking about earlier. What happens to the parts when the container is gone? When the container is destroyed, if the parts are capable of separate existence, then the association is called an aggregation. However, okay, when the container is gone, if the parts are also destroyed, then it's a stronger aggregation, and we call that a composition. So let's look at some real examples. Let's come back to the book. Book with the pages. I tear the book apart, I burn the book, pages are gone. The relationship, a book is made up of pages. What do you think? Is that an aggregation, mere association, or a composition? What's that kind of relationship? What do you think it is? Who said that? Composition? Yep, absolutely right. And why do you think it's a composition? Don't exist without the book. Exactly. Okay, thank you. So the book. What about a human body is made up of the brain? When the person is diseased, when the person dies, what happens to the components, the parts? Again, that's a very interesting question. Can you transplant? All right? If it's perhaps the brain and the technology is not advanced and you can't transplant the brain, it's a composition. Perhaps if you can take the heart and transplant it within the first 1 hour, it's an aggregation. Right? A car is made up of an engine. If you destroy the engine along with the car, then it's a composition. But if you can actually, if the outside of the car is destroyed, the engine's perfect, and you want to actually take that engine and replace it in another car, that's an aggregation. Okay? Give me more. What other examples can you think of? What about when you go shopping, online shopping? A shopping cart is made up of line items, the individual items that you... So a shopping cart, and this is very relevant to your assignment. A shopping cart is made up of order items. What do you think? I'll leave that as an open question for your assignment. What kind of relationship is that? How would you model this in your assignment? What do you think? Think about what happens when you say, delete the shopping cart. What happens? Is that an association, a composition, or an aggregation? I'm sure some of you know the answer. What is it? It's a... What do you think? What's your gut feeling? What do you think it is? First of all, tell me, is it a mere association? No. Okay, we established that. What happens to the shopping cart when you go click on delete shopping cart? What happens to the items inside the shopping cart? They disappear. Okay, so that's your answer. All right? Okay? So you can draw plenty of these examples from your everyday life to analyze whether it is aggregation, a composition, or just a mere association. So how do we represent this in UML in a class diagram? If it is an association between just two classes, it is represented by a solid line. if it is represented by a what I've got over there. So all of those three examples there are examples of association. All right, so actually two examples, the dog belonging to an owner and a professor teaching course. Now I can detail and add more information about the nature of this association. So first of all, the association is modeled by a solid line. Now there is a bit of difference in convention. If you go and Google on the internet, you might see this association modeled as a line with two arrows on either side. I prefer to use, this is the UML reference. It tells us to use a solid line with no arrows. Now, if you want to, optionally, if you wanted to indicate the direction of the association, so for example, you say a dog belongs to an owner, you can use the inverted, the side triangle with which pointing to the apex of the triangle, pointing in the direction of the association. And apart from specifying the association and the direction of the association, you must also specify the cardinality. So how many objects on either side of the association? So one dog belongs to one owner. So that's a one-to-one relationship, a one-to-one association. The next one is it's a one-to-many association, and that's indicated by 0 ... asterisk. Now what's the difference between if I said on the right hand side with the course, if I were to change that from a 0 to star meaning multiple, to 1 to multiple, what do you think that might mean? What's the semantic of semantic inference of such a small change? What do you think a 0 to multiple is? How is a 0 to multiple different to, just think about it, to a 1 to multiple? Any ideas? What a 0 to multiple means is that a professor can teach none or many courses, right? If you put it as 1 ... star, it means that a professor must at least teach one course. Okay? So a subtle change like that. So by saying 0 to the star, it means that the professor may not teach any course. The professor can teach multiple courses. However, if I change that to 1 to star, it means that at a minimal, they must teach at least one course, but they can teach one or many. Okay? On the left-hand side, you have one professor associated with 0 or more courses. A dog is associated with one and only one owner. So the first is an example of one-to-one relationship. The second is an example of what we call as a one-to-many relationship. The third variation we can have is a many-to-many relationship. Can you think of a real-world scenario that could have a many-to-many relationship? Anything out of your practical everyday life, a many-to-many relationship. Just yourself. You as a student, you are enrolled in many course offerings. And a course offering could have many students enrolled in it. Okay? So if I were to model that, I would have a class called as student and a class called as course offering. And I would see a 0 to star on both sides. And it's a bidirectional association because a student can be enrolled in multiple courses and a course can have 0 or many students. Okay? So 3 types of association. So when you model an association in a class diagram, you need to model the class, then you need to show the association with a solid line, Then you can choose to show the direction of the association. And I'm not so particular about the direction, as long as you show me the association and the cardinality, okay, that tells me. Now, when I draw a class diagram like that, where I've just simply stated the name of the class, and sometimes I can show the attributes, but I'm not really particularly showing whether any methods, that's what we call as a conceptual class diagram. So there is a conceptual class diagram, and then there is a design class diagram. A conceptual class diagram is the very first artifact that you will generate as soon as you've done your use case modeling, your sequence diagrams. You're now brainstorming, and you come up with, you're trying to identify all the classes, so you start drawing up these conceptual class diagrams. So you just have the names of the classes, you might have the attributes, and you're showing the associations and the inheritance, but you're not quite there yet to start thinking about the methods that need to go in this class. That conceptual class diagram will eventually evolve into a detailed design class diagram where everything is articulated with clear attributes, clear methods, whether they are private or public attributes, or private or public methods, and so on. Okay? Is everyone clear about association? Okay? All right. Was there a question? Somebody had a question at there? Okay, so we talked about when the association has a container relationship, a whole part relationship, we call it, we give it a name either as aggregation or composition. How do we model that in UML? An aggregation is modeled again by a solid line with a diamond, a hollow diamond on the container side. And this is something that many students get it wrong. So in the exam, if I were to ask you to draw a class diagram, this I find is a very, very common mistake. You know, people draw the diamond on the other side. So remember, it's an association, so it has a solid line. It's an aggregation. I need a hollow diamond. Hollow diamond lives on the side of the container. A lab contains the computers. So why is it an aggregation? It's an aggregation because if the lab is shut down for maintenance, I can still take the computers and relocate them to another computer lab. Okay? So it is an example of an aggregation. At the bottom we have a composition where the contained item is an integral part of the containing item, such as a leg in a desk. And I've used the example of engine in a car, assuming that if the car is gone, the engine's gone as well. But you could argue and say, hey, I can move the engine to another car, then it's an aggregation. Okay, but you get the idea. If the containing item is destroyed, if the contained items are also destroyed along with it, then it's a composition, again, indicated by a solid line, and this time a filled-in diamond that lives on the side of the container. Okay? Any questions? So far, what we have discussed, we've talked about objects, how to generalize objects into a class. Classes have attributes and methods. We initialize the state of the attributes with a constructor. Then we looked at defining instance methods inside the class and defining getter and setter methods on the attributes. Then we talked about relationships between classes. We identified two types of relationships. One is inheritance and the other one is association. If you're modeling an is-a kind of relationship between two classes, that's modeled with the inheritance. If you can't see a is-a type of relationship, then you model that as an association. An association can be further refined as either an aggregation or a composition if it is a whole part or a container relationship. An aggregation is one where the contained item is capable of independent existence. A composition is where the contained item is not capable of independent existence. Okay? And just a few more examples. Okay? Again, the same rules apply in terms of the cardinality. Notice that cardinality is only represented on associations, not on inheritance. So the first one, again, is the example that we've already discussed, which is the car containing an engine. So more examples. So I should edit my previous slide, because on the previous slide I've put the car and engine as a composition, but on this slide I have changed it to an aggregation. So I need to go back and edit the slide and say it depends on the context. The second one, as you can see, is an aggregation. The book is composed of pages. And the third one is a truck is a type of vehicle, and that's an inheritance. Okay? Any questions before we move on and start looking at how to actually do a domain model with this knowledge that we have acquired so far? Very important. You need to be very clear. Okay? Any questions at all? All right. Yes? Why do we see the direction is an optional thing, but sometimes it just brings more clarity to the class diagram to show who's actually be invoking the interaction on the other object. Okay, so for example, when you have an association student and book, for example, and if you want to say the student borrows a book, it's an action initiated by the student. So you want to show the nature or the direction of that interaction, but it is an optional thing, okay? Some conventions do ask you, if it is a bidirectional, some guides tell you that you do actually two solid lines, one solid line representing one way of direction, but I think if you wanted to show a bidirectional, a single solid line with two of those little dark triangles pointing to both sides is fine as well. Okay. Okay, so before I move on to how to create a domain model, I'm just going to switch screens quickly and show you one more thing in inheritance in Python, and then we'll come back to the screen again. Am I broadcasting? Yeah. Okay, if I were to now go print A1 and you can see here what it does, it gives me, when I say print A1, remember A1, we talked about it yesterday, is a reference to an object instance in memory. So when I say print A1, it's just printing me the name of the class that it belongs to and possibly some hexadecimal number that's presumably maybe the memory address. But where is that coming from? Remember I told you that every class inherits a base class called the object? The object class has a method implemented called as the string method, and what it's saying is that give me a string representation. So inside the implementation of that string method, it's just generating the name of the class and the memory address, and it just gives you some output. But sometimes we want a more useful information to be printed when we say print A1s, for example. And this is where method overriding comes in. So remember I told you, if you are inheriting a base class and there is a method in the parent class, you can choose to override the method in the child class or the derived class. So what I can do is I can define and okay, so I can say what do we want to say? Something like has an account with some balance, okay? And dot format, I can go self dot name, comma, self. Now notice here I'm not actually using the getter methods because these are instance methods inside the object instance. So living inside the object instance means that they have access to their own instance variable, so it's perfectly fine to access the instance variables directly without using the getter methods. Okay, all right, I think that is right. So now, if I save it, and you can see that instead of that, the random output that was generated before, I now have a more meaningful message generated. Joe has an account with the balance, whatever the 100 is. Now, what I can also do, I can continue with the overriding, and I can say define, and I can go say, I can go return, and I just want to make sure I've got this return. And same way, if I want to invoke a method in the parent class, I can go, so account.str, and then I could plus with interest, and I can go the, is it called saver interest? Yeah. Okay, and if I now go and print S1, and what did I do here wrong? Tell me something I've done wrong here. And what's the mistake here? Tell me what I went wrong here. I forgot to convert this to a, remember it was a saved as a float, and fix that, and that should work. Okay? So, just go over what I've done over here. So this is a good example of method overriding. The string method is a method that lives in the object class, and you've seen what the output was before. I want to render more meaningful output, so I override the string method and with a more meaningful message. Then I decide to override that in the derived class, which is savings account, but I know that part of the output is already generated in the parent class, so I go account and I call the string method in the parent class, which generates the first part of the output, and then I concatenate it with my own specified output. Okay? All right, any questions? And you do exactly the same. Remember when we talked about yesterday when comparing two object references? And I had a slide which showed you that when I compared A1 and A2, they were pointing to two object instances, and when I used the equality operator, the answer was false because the default behavior of the equality operator is checking if those two variables are pointing to the same object instance, and they were not. So the comparison, if A1 equals A2, returned the result of false. Now what if you didn't want to actually compare if they're just pointing to the same object instance? What you really wanted was to actually compare the contents of the object instance itself. Then what you do, again you use the method overriding, and you go define. By doing this, you would say return. So first of all, okay, I'm comparing myself with another object. So self dot, I can first check the class equals obj dot class and self dot balance is equal to obj dot balance. Okay, so what that's done now, when I invoke the equality operator, I'm no longer going to be comparing the object references, but I'm actually going to be looking at and checking if the contents are the same. Okay, and first of all, I go to check if my current object instance and the one that is being passed in, are they instances of the same class? And that's what this is doing. If self.class is equal to object.class, are they instances of the same class? And then if they are of the same object instances of the same class, you go to compare their balances. Okay? So now, how you implement the equality method comes down to really what the business wants, what is the business semantics in terms of equality. So if I now were to go and define another variable called A2 with account belonging to Mary, for example, with the same balance, and I said print A1 equals A2, if my implementation is correct, and that should return now a true. Okay? If I didn't have the equality method, okay, so let's just get rid of that. And save it. And if I were to run the code, you can see print A1 the equality comparison between the two gives you a false because A1 and A2 are pointing to two different object instances. But the moment I actually override the equality behavior and I said, don't just check the object references, actually check the content for me, then it will return you back a result of true. Okay? Another useful example of how you can make use of the overriding. And you saw another example earlier where you can override the getArea method in the rectangle class to override with its own specialized behavior. So method overriding is something that you will use extensively if you have an inheritance modeled in your class diagram. Okay? All right. Let's move on quickly to drawing up some, actually building a domain model, okay, and we don't have much time left to do that. While I set this up, I'm just going to keep the image freezing and to play with this. If I were to no. Okay, that's better. Okay, all right. What we're going to learn now, so far, all that we have learned about object-oriented design in terms of the classes and the relationships, and we understand how the different types of relationships. And we've also studied use case modeling, and let's see how to actually put all this idea together to generate a domain model. Okay, so let's think of a quick example. For example, let's do an example which is a student borrowing a library. A student borrowing, I'm just thinking loud, a student borrowing a book from a library. Let's say you have been asked to build a library management system, and the library management system wants the students to be able to borrow a book, search for a book, borrow a book, return a book. Okay? So you start drawing a use case diagram for it first. And I just thought I'll quickly go over the use case diagram. The feedback I got back from the tutors is that the students are still confused about the stereotypes and how they all fit together. So let's do a very quick example. I did send out a notice yesterday clarifying a few conventions in terms of the lines. So let's say we had a use case. So for example, I have an actor here, and we are doing a library management system. The actor wants to borrow a book of, let's say, borrow a copy of a book. That's one use case. Now, and return a copy. That's the other use case. Now, the actor will be initiating this. All the initiations is drawn with a solid line. We use the stereotype initiate. Okay? All right. Now, okay. Okay. Maybe there is a librarian who also needs to add a book, for example, and that would be an initiate. Okay? Now, when we borrow a copy of the book, so the student puts in the student ID and they do borrow the book, perhaps you need to then think about you need to have a loan transaction, or you need to record, so this will go and you need to record the transaction, the loan transaction. You want to record the loan transaction. So this is an include, and I'm going to delete that because that should be a dotted line. Okay? So students got confused between the include and the extend. So let me just clarify that. Include means that you have the base use case here is borrow a copy of the book, right? The second use case is when you borrow a book, you must also record the loan transaction. So that's the second use case that must be included as part of the base use case. So that's indicated by the stereotype include, and there is a dotted line. Okay? Now, let's say when the student borrows a copy of the book, they optionally decide they might want a little printout saying what book they have borrowed and when's the due date by. Okay, so print, let's say there is a print record, but that is an optional use case. We use the stereotype extend to indicate that, again, your base use case is borrow, and optionally you can extend the behavior of the base use case by additionally printing a record of the loan transaction. But the question whether it's an include or an extend, the question you need to ask, can the base use case, is the base use case capable of independent existence without the sub-use case? The answer to that, in the first scenario, in recording the transaction, that must be a part of the base use case, so it must be included. But in the second scenario where the print record that is an optional, the base use case is still capable of independent existence without that, so that is indicated with an extend stereotype. Okay? Is that clear? So that's how you draw a come up. So this is a very, very simple, a trivial use case diagram, but that's adequate for our purposes. The next thing what I do is, once you've done the use case modeling, the next thing is I use what we call a CRC technique. CRC stands for classes, responsibilities, and collaborators. Yeah? Yeah? The dotted line is only ever used for the include and the extend stereotypes. All the initiate and the participate are solid lines. Okay? But and also, sorry, the initiates don't have any arrows on their tail, but the include and the extend do have arrows. So with the include, the arrow goes on the side, on the sub-use case which is being included. And with the extend, it's the opposite direction. It goes back to the base use case that is being extended, whose behavior is being extended. Okay, another point. And I think I missed that in the solutions that I posted for the tutorial, so I revised the arrows and I republished the restaurant use case just to fix those little notations there. Okay, all right. So once we've done that, we go on and move to the CRC technique. CRC stands for classes, and let me tell you why I'm actually drawing this up. And we have R for responsibilities. And on the right-hand side, you've got collaborators. Okay? So the CRC is a very, very commonly used, in fact, it's more commonly used than your use case modeling, more so in the agile programming. The agile software development, where we tend to use more user stories instead of use case modeling, they do the requirements analysis, they write up the user stories, and from the user stories, they go into the CRC. And the CRC technique is basically, who's done debating? Have you seen those little palm cards that you have? Those 4x6x4 palm cards. And those are really your CRC cards, okay? So little cards, and why it's so popular is that you can actually spread them on your conference table, and you look at the user stories, which are really your problem requirements, and you do a noun-verb analysis. And as you do the noun-verb analysis of either your use cases or your user stories, you pick the nouns that you come across in the problem statement, and these generally map to your conceptual classes, and your verbs become your responsibilities. And you start writing up these cards one after the other, and you actually lay them out on the table. Sometimes we actually pin them up on the board, and what's really nice about them, you can actually shuffle the way these cards are actually laid out, and when you're done with them, you just throw them. That's it, okay? So they are really a very popular technique for brainstorming and evolving your use case model or your user stories into a domain model where we sit down with a group of developers and architects and the domain users, and we brainstorm, we look at the user requirements, and we come up with a set of classes and responsibilities. So let's just looking at that. Here, I also want to go back to this use case. I said here there's an actor here called borrower, and perhaps I can use a generalization, and the borrower can be perhaps a staff. I'll just drop another actor, or the borrower could be a student. Sorry, my arrows are okay. And that information is going to be very useful to us when we draw up the class diagram. So coming back in here, what's the first, I'm looking at my user story and I'm saying a borrower borrows a copy of the book. So just look at that requirement. The borrower borrows a copy of the book. What are the nouns in there? What are the nouns? Borrower? Yes. So I put the name of the class in here. I call them the borrower. Okay? What are the responsibilities? So the responsibilities are two things. One is you intend to do something, and what's the information that you know? So a borrower, they know their name, their student, maybe their ZID, and they need to borrow a book copy. Okay? So looking at that statement again, a borrower borrows a copy of the book. So what's the other noun that we have there? The book copy. So the collaborators. So you can see now, you can start doing the book copy. All right? So this is where you've drawn remember what the domain model is, okay? If you recall our lecture 1 or lecture 2, we said that what's the difference between the domain model and the use case? This is the system that you're building. What the use case does is it's establishing who's interacting with the system. Now what we're trying to do using the CRC technique, you're trying to find out the components inside the system. So you're looking at the components inside the black box that need to work together, that collaborate together to deliver the behavior that's required by the actor. So in order to borrow a book, the borrower needs to collaborate with the book copy. So that means that I now have another CRC card, and I'm going to call it the book copy. The book copy, what does it know? It knows whatever, it's got I don't know, an ISBN number or something, or maybe, and it's actually going to, remember this is a copy of the book. So I've got a book there which is called Discrete Mathematics Volume 1 by some Albert somebody. Now, the library might actually have about 20 copies of that book. So the book copy, so when you're actually trying to figure out how to actually work out the pieces of the puzzle inside the domain. So now perhaps the student, before they borrow the copy of the book, they actually go and do a search a book, right? And that's another initiate. Now when they do a search for the book actually tells them we have the book in this library, and there are actually 10 copies of the book, all right? So what we're really coming up with, the book is actually associated with another class called the book, because the book itself, what does it know? The book is the class. It collaborates with you can say, so you have, it knows the title, it knows the author, okay? Now, this is not going to be perfect, okay? Now, you might say now, hang on a second, that's not actually right. Maybe that is right, but hang on a second, what does the book copy do? What does the book copy actually collaborate with? So let me go back to the process, what actually happens inside. So then we go back and see the actor is borrowing a book, so they're going to be searching for the book, if the book's available, if the copy is available. Then when they borrow the book, there's actually going to be a record of the loan transaction created. So there is perhaps another collaborator called the transaction record, for example. Okay? So now the transactions, this gives me another class called as transaction copy, a record, sorry. And what is a transaction record? The transaction record, what are the responsibilities? The transaction record, it records the copy of the book borrowed. So it's going to collaborate with the book copy. Okay, so you can start seeing how you can actually piece together. And one more thing I should mention, another mistake that was being done in the labs as I walked around, some of the students, they are forgetting the purpose of the use case diagram, okay? They think that the use case diagram is supposed to model the sequence of events that happen. Now, remember, that's not the purpose of the use case. If you want to model the steps of the use case, you write out a usage scenario and you can model that using a sequence diagram or an activity diagram. A use case is simply supposed to state what are the goals of the user. It is not supposed to have a workflow process. So for example, in the context of your car rental, it shouldn't have a workflow process like search for a car, followed by booking a car, followed by payment. That's not the idea. You're not documenting the sequence of events, you're documenting the goals and who's invoking the goals. And then as you try to work out the piece of the puzzle, how does that goal actually gets accomplished? That's when you start thinking about what are the components collaborating to make that event happen. If you wanted to document how the event is actually happening, you use a different UML artifact like a sequence diagram to do that. And then when you go into the domain model, you start working out what are the entities inside that make the borrowing. So let's just go back to this use case of borrowing a book now. So I've come up with, so when a student tries to borrow the book, they are trying to search for a copy of the book. So they're going to be collaborating with a class called as the book copy. Once they know that it's available, they are going to say, I want to borrow the book, and that's actually going to create a record, the loan transaction. So there is another class called a transaction class, and what does that do? The transaction class, let's just go back in here. This transaction record, what does it need to do? It needs to record who has borrowed what. So it's basically, this transaction record, it knows it knows the borrower, it knows the book copy, and it also knows the due date. Okay, so it's going to be collaborating with the borrower. Okay, so you might decide to go back and see, now, does the borrowing class need to directly collaborate with the book copy, or they actually go back to the trial? Now this is something that can change, but you've got your preliminary CRC modeling where you have kind of established your conceptual classes and you know their responsibilities and you know their collaborators. Okay? So now what you can do is you take this away, and if I can flip over and going to go so let me just, can I do this? Do you see both? Partially. Okay, so let's now draw up the class diagram for it. So let's go to do a conceptual class diagram. So we're going to do a borrower, and we can do a transaction record. And what are the attributes inside the transaction record? It's going to record, each transaction is going to record the student ID, the copy, the book copy, I don't know, like an ID number, and then, sorry? Is that better? Yep. Okay? So what we're going, thank you. So, and that's the due date. All right? So the borrower so you could say the borrower is associated the transaction record, and the transaction record is associated with a book copy. A borrower can have one or more or zero or more loan transactions. So one borrower. The attributes here could be the ZID, for example. And a transaction record corresponds to one and only one book copy. And then we go back and say, we look at the use case diagram and we say, hang on a second, we had a borrower, it could be a staff or a student. So I kind of see an inheritance in there. So I can now go inheritance and I can say student and staff. Okay? Now, just because the use case generalization said there are two types of actors. Now, from a use case perspective, it's important to know who the actors are, who will be interacting with the system. But just because we have two types of actors, it's not necessary to model that in a class diagram. You only do that if you think staff and student have to be modeled with more specific attributes or methods. Okay? And let's assume that there is some more additional things that a staff can do. Perhaps they can have borrowed the book at an extended period of time, or they can do something. They've got some additional behaviors, so you decide to have a subclass. Now, then I say, okay, hang on, then there's another one called as the book copy. So then I also have from my CRC, I've got another class here called the book. Okay? And the book has the ISBN number. Then you have the title. You have the author. Maybe the book copy is not the... Does the ISBN number go by each copy of the book, or it goes by the book, isn't it? No, it doesn't go by the thing. Okay, so you might have something. So you'll come up with whatever the attributes are for the book copy. So let's look at the relationships. A book can have multiple copies. So there could be, let's say if the library, you had a rule that if you had a title, you must have at least one copy of the book. So you could say one book is associated with one or more copies of the book. A borrower can be a student or a staff, and a borrower can have one or more loan transactions, and each loan transaction will be associated with a book copy. Now, a book, perhaps you decide to do some inheritance in there, and you decide to have them as magazines, and you could have that as textbooks or anything like that, and perhaps there is some past papers, past paper or journals. Let's call it journals, for example, or papers. Okay? So you can see how we can start building the class diagram. So this is what we call as a conceptual class diagram. So let's go back. So you've done the use case model. I repeat, the purpose of the use case model is just to identify the actors who will be interacting. So you look at the outside view. What do you want the system to do? That's what a use case model is. So do not be confused and try to model the events that happen during the execution of the use case. That's a sequence diagram. So from the use case, you have said, what are the services that are needed? The next question you ask, How are these services provided? How is it accomplished? The answer to the how question is when you start doing the domain model. And to do the domain model, the first thing that you do is the CRC techniques where, based on the use case diagram, your user stories, you try to do a noun and verb analysis, and for each class, you start drawing up a CRC card. So with the CRC technique, you're trying to establish the classes, the responsibilities of the classes, and the collaborators of that class. When you're doing the responsibilities, you do two things. You figure out what information do I know. So as a transaction record class, I know the copy of the book that's been borrowed, I know the person who's borrowed it, and I know the due date. Who do I collaborate with? I collaborate with the copy of the book. Okay? So once you've done the classes, responsibilities, and collaborations, you then take away, so at the moment when you're doing the CRC, you are just still at you know that you've done the collaborations, but you still do not know if that collaboration is just a mere association or an aggregation, or it is a composition. This gets further refined in the class diagram, okay? So you can say, for example, if I had we didn't have this in a class. Let's say you had a class called as library, and say the library is made up of books. So I draw the triangle here. One library has one or many book copies, and you can use that is an aggregation. Okay? And so that is now your conceptual class diagram. Okay? And that's what you are expected to produce for your assignment 1. You will need to do the use case diagrams. In your lab exercise next week, for the car rental system that you had developed the use case diagram, you will be doing the CRC cards, and you will be doing a class diagram, a conceptual class diagram for it. Okay? And in your assignment, again, you have the same conceptual class diagram. For a conceptual class diagram, I don't need the methods. All I need to see is all the key classes. So you must have done a thorough CRC technique analysis. You need to have all the classes. Show me the responsibility. So you should need to, on the CRC, you can show the responsibility. Now you don't do CRC for the assignment. Okay, I'll take back what I said. You do the use case diagram, you do the conceptual class diagram. Conceptual class diagram will have all the key classes. It should show the inheritance, the associations, if any, and the associations should be further refined as mere associations, aggregations, or compositions, and then it needs to show the cardinality. Okay? And the attributes. Okay? All right. I will quickly go and talk to you about the assignment. We have 5 minutes left. I mean, the assignment is the requirements. So I've actually done the requirements analysis for you. So in the sense, all the requirements are clearly stipulated. You are required to produce a set of use cases, and you develop a domain model, and you must draw these artifacts using draw.io. And you will get some practice using draw.io next week in your labs. You are required to produce the class diagram using draw.io. Okay? And there's detailed instructions in your lab that's been released as to where you can, how you can actually upload. It's fairly simple. So just quickly going through, have you all read the assignment spec? Do you have any specific questions? So basically what you are going to be doing, you are modeling an online shopping system. This shopping system is going to be used by an outdoor camping, clothing and camping gear store. So it basically sells two kinds of items. They are clothing and camping gear. As you go through the requirements, you can, now that you've got this knowledge in here, you can start thinking about the use cases, and you can start visualizing the use cases. From there, you can start thinking about the domain model. So the inventory stores all the items. Every item in the store has a name, product, and a price, product description and a price. Then there are two types of categories. There's clothing and camping gear. Clothing items can be further subdivided into shirts, pants, jackets, swimwear, boots, and accessories, which encompasses a lot of things like gloves and beanies and things like that. And they're all under accessories. Clothing items, in addition, have two additional attributes, size and color. The allowable sizes are small, medium, and large. The color is provided as text, and the camping items will have two additional attributes called dimensions and weight. So just reading those set of requirements, you should be able to start conceptualizing. Think about okay, what is it that I want to do? What is the domain model going to look like? What's the class diagram? Do your noun-verb analysis, okay? Then what can the customer do? So these are basically the online shopping system. When you're thinking about the use cases, what can I do with this online shopping system? You should be able to maintain the inventory, search the inventory, maintain periodic discounts. Now, searching the inventory is pretty straightforward, allows a customer to search all the items that's currently stocked. You can do a search by category or by the subcategory. Now, the discounts are a little interesting in here. We have, each product will have an individual or a group discount, okay? Now, the flat discount is like when you go into Woolworths and you shop for something and you see something like half price it's $20 off, okay? Or a percentage discount, everything is 10% off. All the pens are 10% off the base price. A group discount is what we call a buy one, get one free strategy. Now there's a little bit of flexibility on how you actually want to interpret this, but the idea here is it's like when you go into Woolworths, when I buy 2 cheese biscuits, I get the 3rd cheese biscuit free. It's the same idea, okay? So you buy multiple items and one